So our final presenter today is Mr. Garrett Shields. He is the UAS National Program Manager for AMEC Foster Wheeler. He is responsible for UAS operations, procurement, training for 50 office locations around the U.S. He is a graduate of Appalachian State University, so we don't just import people who know about UAS. We grow some of them here. With a degree in geography and GIS as well as GISP. He's also a FAA licensed remote pilot and certified floodplain manager. Garrett?
So one thing I've noticed about conferences like this is they always stick the big guy right up next to the meal. So I promise you, I'm not going to keep you away from lunch. So we'll be brief on this. So we've seen a lot of great presentations so far, really attesting to how far this technology has come and what is really possible with it. And we've seen an academic application, we've seen the software application. So now I bring the commercial and the commercial applications to this. And this is kind of what I wanted to bring and talk to you guys about, was really the what is possible from a commercial perspective, and where this data is going and how we can really produce some high quality data sets from this new technology. I'll talk a little bit about myself. That wasn't already said. I am the National Program Manager. AMEC Foster Wheeler started our UAS operations actually in Canada about 4 years ago. We've been using drones pretty regularly up there. Our program here in the U.S. started in an unofficial capacity about 2 years ago when we began looking at the technology, really developing an action plan. One of the things we wanted to make sure of was, before we ever flew our first mission, before we ever collected our first data point, that we really understood all of the aspects of this. Not only the regulatory aspects, but also the safety concerns that are brought up. Obviously, you have robots flying around in the sky. There's a safety component to this. There's things with the FAA we have to look at. So these are things that we took into consideration before we ever purchased our first UAV. Our operation started about, actually right around the date of Part 107. As many other companies, we did apply for a 333 exemption in 2015. While it was in review process, Part 107 came about, so we have been operating under those guidelines ever since. So what I wanted to talk to you guys about really is a little bit of a play and a continuation of what we've heard so far, is what's actually possible with the UAV. What data can you collect? What types of data sets can you produce from it? And kind of bring a little bit of a commercial point of view behind it and what we've been using for. I won't bore you too much with the details. I think everyone in this room knows what a UAV is and knows what's possible. From a commercial perspective, what we really run into is it's a cost savings and also an efficiency aspect that goes along with UAV. Traditionally, what we've been doing in the past, we've been relying on these traditional manned collection methods. So either an aerial method or a terrestrial method. We'll either send folks out in the field with with laser scanners or field survey equipment, or we'll have folks going around with airplanes or boats, and we're collecting data in a manned way. Now, these are all fine and good, and that technology is advanced and is very mature and is still moving forward. But what we found now is we can do this at certain scales at even faster and higher resolution with unmanned systems. And I'm going to focus mostly on the aerial aspect of it today. I could talk for days if we want to go into ROVs and maritime and everything else that's possible with an unmanned system. And the technology, I think, today has really produced, it has really come up with ways, the technology is advanced in ways that we can have broader commercial application. It's democratizing how many people can use the technology. Prices are coming down for sensors and aircraft, and it's really making it where a lot of different people can use the technology in very different ways. Beginner Drone 101, I won't spend a lot of time on this, but we really have two main categories. I wanted to focus really on what the difference in capabilities are from an acquisition standpoint. Obviously, we have fixed wing, we have multi-rotor. Really, when we're planning missions and when we're looking at what we're going to use, sensor payloads on both rotary and fixed wing UAVs are almost equal now. The only real difference in sensor payloads, a lot of times you'll find some multi-rotors have a heavier lift capability. A lot of times a fixed wing, it's a lighter weight aircraft. That's why it can stay up in the air for 45 minutes to an hour or more. So the sensors tend to be a little bit smaller. Some of your heavier, big multi-rotors can lift 10, 12 kilos or even more and still stay within that 55-pound rule that the FAA governs as a small UAS. Whenever we're planning missions, determining which UAV type we're going to use is really just basically we look at the characteristics of the flight. If we have to collect a very large area, we're typically going to go towards the fixed wing application. A smaller area, we would tend to lean towards a multi-rotor aspect, and also depending on what the characteristics of that acquisition area are. If we have a strict boundary, so for instance, if we're flying in a park or somewhere and we're collecting data and there's roads on either side of that park, even though it may be a large park, we're not probably going to use a fixed wing because you have to account for flying over people, which is not allowed under the FAA rules without an exemption. If I don't have a special exemption for that area to fly over people, a fixed wing solution may not be the best thing to use because you have to account for the turnaround zones where the drone has to go out and collect outside the area to come around and do the next flight path. If I have a fixed wing solution, I can program the flight path to where it actually stops right at the boundary of my flight zone, turns around and comes back. So whereas I may have to do a few more flights because of the shorter endurance of a multi-rotor, it's actually the more precise application for that particular mission site. So before I get into the example, I wanted to talk to you a little bit about just a broad overview, 1,000-foot overview of some of the different applications of UAS that we've been using and what we're seeing in the industry. Obviously, from a commercial perspective, we're an engineering design firm, so anything to do with infrastructure and building inspections is an automatic win with the drone industry. We send people up to inspect towers, water towers, high up infrastructure, bridges. That presents a significant risk to a human being. Even though we have lots of safety equipment, we're always safety conscious, there's always going to be that risk. And it's going to take a long time. You have to send somebody climbing up a 400-foot water tower. It's going to take time for them to get up there and do everything they need to do. These things can be done much more efficiently and quickly and safely with an unmanned application. And the photo that you see up there is actually a mining pit that we fly monthly, and those are the photo doesn't do it any justice. That's actually about a 60-foot sheer cliff. So sending a human down to inspect the mine pit and to look and see what's going on down there is not very ideal because you've got a very hazardous zone there. Obviously, we've talked about orthophotography. We've seen the true applications of that in the first presentation of how detailed you can really get with ortho photos and aerial imaging with a UAV. We're typically running on our orthos somewhere around the 2 to 5 centimeter pixel resolution range. Again, it's depending on what camera we use and how high we fly. But I mean, you can see license plates when it gets down. Not that we were using to spy on license plates, but that's how detailed you can get with imagery that fine. We can also go into multi and hyperspectral imaging. Hyperspectral is possible with UAVs. It is still kind of in a development stage. The sensors are starting to come around. The algorithms are being produced right now. We work with a couple third-party firms that are getting into that space. So I'm really excited to see how hyperspectral imaging really changes how we go about really targeting certain aspects of imagery to pull out meaningful information. Right now, multispectral is very possible with color infrared, near infrared, false color. We can use those for vegetative indexing. The precision agriculture industry has been using drones successfully in this field for probably the last 2 to 3 years in various stages, looking at plant heights, plant counts. You can also add thermal, which is the next part of the slide. Add thermal capabilities. You can obviously look to view habitat. You can look for habitats. You can go and do search and rescue missions from an emergency management perspective. And also you can use it for environmental applications. You can use you can use thermal to look at plant health, soil characteristics, the soil temperatures that help you with yield, with plant yield counts, and also for utility inspections. We work a lot with utility clients inspecting solar farms or gas or utility systems. It's really helpful having that sensor capability. The great thing about everything I've talked about is so far, sensors and UAV technology has advanced so much that everything I just talked to you about can be done with one UAV, which is amazing to me. There's the different number of sensors and cross compatibility that are out there now. You don't have to have this massive fleet of specialized UAVs, which for me would be great because I'm a kid in a candy store. I like going to the toy store and getting all my toys. So I'd love to have a UAV for every specific thing, but my boss would kill me because I'd be spending way too much money. So what we look at is versatility when we're looking at hardware. What can we put on one UAV to maximize what we actually can do? And these last ones, obviously, volumetric calculations is very easy with photogrammetry. You can do estimates of stockpiles, cut and fill analysis. Surface water sampling is something that we actually got into at the request of one of our clients. It was something that I hadn't even thought about when we were looking initially at our program. We have areas where you have to go and collect environmental samples that is actually now impossible or very ill-advised to send a human being to go do. So we have certain clients that have regulatory requirements to collect water quality samples on a monthly or quarterly basis. Some of these zones you can't send a human being down. So you still can't send a human down, but you still have to get a water sample. You're left with very few options. So we actually were approached by one of our clients to start researching a way to efficiently collect water samples with a UAV. This is not a specific picture of one of those, but it's a very similar aspect of what we're doing. So it's really something that shows that your imagination is really as far as you can go with this technology. There really is no limit to what you can do. Everything can be done safely. Most things at least can be done legally. So you just need to check with regulations, check what you're doing to make sure you're doing everything properly. And then we also have LiDAR and photogrammetry, which we've discussed in all the previous presentations in this session. LiDAR is becoming much more widely available through UAVs. The sensor technology is starting to get smaller, lighter. There are several UAVs that can hold a LiDAR sensor. We partner with a company that does have that capability. We're looking now at 50 to 100 points per square meter, 120 in some cases where we have good overlap for this LiDAR. So you're looking at extremely dense LiDAR from the air, collected somewhere around 180 to 200 feet up. So you can really get into some very detailed data sets with this. And we've, of course, talked about photogrammetry, which is where I wanted to get into kind of my case study. What I wanted to really focus on was how we can use UAVs, unmanned technology, in conjunction with existing technology to produce faster, more efficient, and much better data. So what we did, we had a case study where we went down to Collier County, which is Naples, Florida. We partnered with Autodesk and a local firm here out of Salisbury called Sane Technology. We went down and we all kind of descended on this wastewater treatment plant at the request of the county to come down and kind of do a proof of concept on their wastewater facility in Naples. What we were going to do is they wanted to find a way to produce a digital as-built without having to send your surveyors and your measurers out there to spend a lot of time collecting all the measurements and doing everything in the field, which is the traditional way. They wanted to see, is there a way we can use unmanned technology to really advance how this is done? So what we did, a little bit of a brief on the mission area. So this was at the wastewater treatment facility in Naples, Florida. We collected over a course of 2 days. This was in July of last year. Even though it was in South Florida, there was actually no airspace issues here, which is one of the things we always look at when we start a mission, is what are the airspace requirements and when we need any kind of special permission to fly there from the FAA. The picture on the right is kind of the Google image of the area. It's about 10 acres grand total, lots of above ground tanks, above ground facilities. So really good chance to go and collect some good data in these sites. What we used, we had a variety of different equipment. We actually used 2 separate UAVs on site. We had you see the pictures there. We've got 2 DJI drones. We had one Inspire 1 Pro with the micro 4/3 camera on it, and then we also had a Phantom 3 Pro, smaller sensor, so we used that for a little higher level overview, whereas we used the Inspire with its larger sensor to collect a lot more detail around the edges and around the tops of the buildings. We also coupled that with a traditional terrestrial LiDAR scanner. One of the things we were trying to do was collect the building in an accurate 3D sense. So traditionally, when you're doing photogrammetry of large areas, you're doing the structure from motion collection. You're just using kind of a top-down or a slightly oblique approach with the UAV. Because of the level of detail of some of these buildings, you've got lots of pipes, you've got lots of structural details on these buildings. Taking photos was not going to be enough, and we recognized that from the beginning, that there were going to be certain things that were not going to be captured from that initial photo. You're going to have trouble getting in behind things. You're not going to get all the detail that you're going to need to really complete a digital as-built from this. So we brought in that laser scanner to help augment the photos and the photogrammetric approach from the UAVs. And then we also brought out our survey crews from South Florida to come and do the ground control and the validation as well. We collected for a day and a half. Over the course of the day and a half, we collected just shy of 1,100 photos for this one particular structure that I'm going to show you. We did 51 separate laser scans, so a absolute crapload of data. We ended up with about 569 million data points, which is basically painting every horizontal and vertical surface of these buildings. You can think, when you do, I come from the aerial LiDAR world. We work with a lot of different companies doing large scale aerial collection. 569 million data points for me, that could be a county. This is a building we're dealing with. So the amount of data was just absolutely phenomenal. And one of the things that was special about this project was not necessarily not just the technology that was used, but also how the photogrammetric data was collected. Traditionally, we would see you go out and you pre-program in your flight lines, you set your overlap, you fly a gridded mission, the drone comes back, lands, everybody goes home. We went through a much more detailed method, and we actually collected photogrammetric data manually. We had some amazing pilots come out and fly that day. They're very, very highly skilled in what they did. And they actually flew manual photos of the whole area, moving kind of in an orbital manner, kind of creating a dome of photos on either side and up and down each side of the building. This is kind of a representation of where those photos were collecting. You can see it's not a perfect grid line. So these are all spiral. These were all taken kind of in a spiral sense. We started at the lower end, took photos, and then they would come back at the starting point, move up a little bit, take more photos, and go all the way around. This one building took, I think, about an hour and a half of photo collection with both drones going at one time. So you can see the mesh that was created from that. Once we took this mesh and coupled it with all the LiDAR scans, the laser scans, we end up with this final product, which, for those of you in the front of the room, you can see this is not a photograph. For the folks in the back of the room, this is not a photograph. This is the actual 3D color model with the RGB values from the overall ortho stitched onto it. This is what is possible with UAV technology. This is not LiDAR. Well, it is LiDAR from the ground, but this is what is truly possible when you get into high detail photogrammetric collection. We took the ground control points, which were shot both on the ground and at certain points on the buildings, because we wanted to make sure we stitched this down and nailed it down to every surface on all three axes. So we put some ground control points and shot values on the actual structure itself. We made sure we hit some of the landmark stuff. So some of these, like the sign on the building, we knew exactly how wide that sign was from the building plans. We knew how big the doors were. So we shot ground control points in areas where we knew we could go back and validate it. Once we did the final validation, our surveyors took a look at it. We ended up with 1.6 centimeters was our average accuracy of this structure, which is, to me, is amazing. Which really validated to me and to several other folks that if you take the time to really plan out something and do it correctly, you can get extremely accurate results from a combination of UAV and laser scans. Typically, when we're doing photogrammetry from just a drone by itself, we would typically, I personally would shy away from areas with any kind of vegetation, especially if I'm trying to do some kind of terrain adjustment, because that vegetation is going to skew it. I tend to go for bare earth or bare dirt, bare rock. where we've seen in previous presentations that it's a lot more accurate because you're getting points directly on the ground. There's not a lot of distortion. But this had every possible obstacle you could think of what could possibly distort a photo. You have lots of features, lots of different things that could get in your way, and we managed to get every last bit of it in 3 dimensions to create a really, really tight 3-dimensional model. We did eventually go back. We had enough data to collect the entire wastewater facility. I don't have that up to show because it was honestly the data was just too big and my computer acted like it was going to catch fire when I tried to show it, which is something else you have to take into account. We did have a few special considerations, things we had to look out for. Obviously, weather being the biggest factor. This was South Florida in the middle of summer, so it could be sunny and beautiful one minute, and the next minute you're ducking for cover because you almost got struck by lightning. So we had to be very cognizant of the weather. Airspace was an issue. Fortunately for us, it wasn't. South Florida has a lot of controlled airspace, a lot of major airports, but we were good. We had to take into consideration the county personnel. They still had to do their jobs. They were non-participating personnel, so we had to make sure that we had this area excluded to where we're not flying over any non-participating people and keeping it safe. Also, we had to deal with wildlife. I'm sure some of you have seen YouTube videos of police in Austria training hawks and birds of prey to take down drones. Well, this little guy was sitting right there watching us the whole time. So we had to keep in mind, make sure that we didn't disturb the osprey's nest. There were several other birds of prey that were nesting on site, so we wanted to make sure we stayed away from them because we really didn't want to explain to people why we had a dead osprey and a crashed drone. Just not a good idea. And then we also had to make sure that we had the proper levels of overlap, since we were coupling together 2 different data collection sources with laser scanning and with photogrammetry from the UAV. We had to make sure that we had enough overlap in the initial collection to marry those together very accurately. There's a lot of words on this slide. I'm not going to go through them all. Basically, what I wanted to kind of sum up with a little bit are what we've seen are the cost benefits of doing an unmanned collection effort versus a traditional method. This particular survey, we estimated after talking to some of our engineers, saved about 45% on time and labor based on the amount of time it took to collect. Doing an as-built on that one structure using traditional methods would have taken several days on site, if not a couple weeks. We managed to do all the collection in about 16 hours worth of time in the field, so about just under 2 days total. What we're seeing around the board with unmanned collection is that we're looking at usually about a factor of 10 reduction in cost. Sometimes I won't say that for everything, but we're looking at a typical aerial survey collection for us of just a small area, somewhere between $5,000 to $10,000 on average. I'm not quoting any pricing here, but just in a general range, versus you take into account a manned collection where you have to deal with fuel costs, mobilization, they're a lot higher. Your costs can be somewhere anywhere from $15,000 to over $100,000. Also with UAV, we have to consider airspace and any kind of permissions that we'll need with that, with FAA regulations, which again, more words, I'm not going to go into them. For anyone who operates commercially, or if anyone has any desire to operate commercially, these are your rules. This is the FAA Part 107 rule. In a nutshell, don't fly within 5 miles of airports or within controlled airspace, stay under 400 feet, maintain line of sight. All of these things govern everything that we do. Now, all of these things can also be, you can have an exception to these if you prove to the FAA why you're going to operate safely. If you can't operate within these guidelines, you can apply for a waiver with the FAA to be exempted from some of these regulations. Not very many companies have successfully done that. The FAA is still in a state of trying to figure things out because they're, I think, frankly, overwhelmed with the amount of drones that have entered the airspace in the last year. I will end with what the last presentation ended with, because I do sit in that commercial acquisition world where we are selling data and selling services. So make friends with surveyors. Surveyors are our friends. They've always been our friends, and they always will be our friends. As was mentioned before, NC law does require a survey seal for any data collected that is considered measured. So ortho photos, topo, photogrammetry, LiDAR, anything that you can derive a measurement from is going to require a survey seal. So what we do from the beginning of every project we start is we engage our surveyors from the start to make sure that they understand the scope of the project, how it's going to be processed, and what the final deliverables are going to be, because they're ultimately going to be the ones signing off on it and having to seal the data. So we make sure that we engage them from day one, and I encourage everyone in the room who is working commercially or has any aspirations for working commercially to do the same. Make friends with a surveyor. Either hire one, use the one you've got, or look to subcontract to a surveyor to make sure that all of your products are sealed and validated as required by the law. And this is any state, truthfully. North Carolina is a little bit more strict with that than other states, but I would still argue that regardless, you need to engage a surveyor to make sure that your products are accurate and validated. And with that, I'll take questions. No, actually, those the UAVs that were used on this project, the most expensive one retailed for about $4,000. So what we've seen is you can spend a lot of money on UAVs. You can spend a lot of money on hardware. The more expensive drones, a lot of times they have a little bit better GPS unit. They may have RTK on them. But really, the accuracy of your data is not only going to be determined by the flight characteristics of how you collected, but also in the amount of ground control that you provide. If you don't have enough points to stitch that data down and validate it, it doesn't matter how good your equipment is, in my opinion, it's only as accurate as the survey that validates it. So you can have a fairly low entry point in cost on the UAV side. Sensors, a lot of these UAVs actually come with them. The camera that the Inspire was using, which was a larger UAV, that sensor was there about $1,800. It's a micro 4/3 sensor, so it's one of the larger ones that you can get for a UAV. It's basically the same frame size that they use for movie cameras, so you get a lot larger pixels. Some of them come with it. LiDAR sensors tend to be a lot more expensive still, 30, 40, 50K, but some of the other ones are. Thermal, I can't speak to hyperspectral. I don't know off the top of my head. Thermal, there's some solutions. One for DJI that ranges anywhere from about $6,000 to $10,000. There's some other ones that run about that same range. The ones that I don't know the specs specifically, but I do know the one sold by DJI was actually manufactured by FLIR. So they've done all the original. They use all their calibration for doing the spot checks on all the temperature ranges. The of thermal. Mm-hmm. Right. As far as thermal goes, we haven't actually used thermal for collecting large-scale thermal imagery. We've been using more in an inspection application, so flying over and just literally looking for hot spots. As far as regular orthos, depending on ground control, we're usually getting somewhere in between as far as 2 and up to 10 centimeters, depending on. I can't really speak too much to thermal though. Mm-hmm. Yeah. So ours has been more inspection based. The 3 companies that I'll rattle off on top of my head, one are DJI, They're a Chinese-based company. 3DR is also a very good company. They're US-based. And then I would say Precision Hawk is another good one. They manufacture a very good fixed wing. And the fourth one would be, I'll add a fourth one, SenseFly is the other one. That's what we've seen in the first presentation was the EB drones. Those are also very good. Who fixes them? That's a little bit more subjective. I know some of the manufacturers offer warranties and care plans if you do have an incident. There are also a lot of third-party companies that will do repairs obviously at certain cost. I'm fortunate so far I haven't had the need just yet, but we do work with one of our distributors here locally who sells us some of our UAV equipment, does in-house repairs as well. A lot of times you would need them to be manufacturer authorized because they can get all the OEM parts if need be. I'm sorry, I couldn't. This particular one that we're looking at was just surface water sampling. So what they did is, it's actually a little funny. We took a 300 milliliter baler, surface water baler, and attached it to the bottom of a Phantom 4 unit, put about 3 meters of line on it, and basically you just fly down to the water surface, dip down to about 3 meters above surface, let the baler fill up, bring it back up, and then we have a sterilized container that we will bring the drone overhead, drop the baler down into that sterilized container so we can go do it again. There's other UAVs we have that have a little bit heavier lift capabilities. The Phantom 4 had about a 1 pound capability, so we're limited to a smaller one. If we need to collect at depth, I would use one of our larger units so we can add a little bit of weight to the unit so we can get down to a specific depth, and we can use the line width, the length of the line, to really determine how far down we go if we need to collect at depth. So the lowest altitude you can collect at? I typically don't go much lower than about 120 feet, just because once you get below a certain point, you're really creating a lot more data than you have to. And you get down to a certain resolution where the camera is not going to get any better. You have to collect at what the optimal distance from the ground that your camera can look at. So once you get below a certain amount, you're not really doing yourselves any favors. You're just really making it harder. Also, collecting at around anywhere from 150 to 200 feet, you're more likely to avoid obstacles like trees and power lines and things like that. You want to be well clear of those as well. Now, for this particular example, we were collecting as far down, since this was a structure, we got down to probably about 8 or 9 feet from the ground, but we were shooting straight out. So we were still about 50 feet back from the structure when taking the photos. But for large scale aerial collection, I would say no lower than about 120, 150 feet. All right, thank y'all.